Hi everyone, it's Miss Butler. We're going to talk about density today. So the general formula, or the definition, if you want to think of it that way, for density is it's the mass, so the amount of matter divided by the volume. So it's basically how much matter or how much stuff divided by or how much is fitting in a certain amount of space in a certain volume. Okay, so for density, when we are solving, we are going to definitely care about units. So let's talk about mass. Well, we know that mass in chemistry is measured in grams. So we're going to take the grams divided by the volume. Well, we can ask ourselves, what are some units for volume? Well, in our class, we use a graduated cylinder a lot to measure volume, and that measures in milliliters. So if we take the mass, which is grams, divided by the volume in milliliters, that will give us our density. Notice grams and milliliters are not the same unit, so that means for density, the actual unit that we put is G/ml, grams per milliliter. The other option you might see is that we could measure the mass in grams, but I know all of you love geometry so much, you may have seen, this is my sad effort of drawing 3D. Can we all just pretend for a hot second that that's a 3D box? Yikes. This is why I don't teach geometry. We'll go with that. Close enough. No, I can't even handle that. Hold on. Eraser. Like this, right? That was way better. Should have done it like that the first time. Anyway, so if you're in geometry, your teacher's like, hey, find the volume of this Kleenex box, or whatever it is, you're going to take the length times the width times the height. And let's say we measure the length in centimeters, the width in centimeters, and the height in centimeters. When I do length times width times height, my unit is centimeter cubed. So that's another way we can find density, and we usually use that for like regular shaped objects, right? Length times width times height, and the unit will be centimeters cubed. So both of these will be units for density. So it says, for each of the following, decide which block is more dense, the orange or the blue, or sometimes we might not be able to tell and explain. So I'm going to pause the video and kind of make some drawings for A and B real quick. So I'll be back in a second. All right, so I'm going to look at A first and kind of talk through my thinking here, and then hopefully you can figure out C and D. But here's what I'm looking at. I know that density is equal to the mass divided by the volume. So let's look for A at the masses. These two blocks are on a scale, and we know that heavier things with with mass, are going to push that scale down. So looking at the orange and the blue, it is obvious that the orange has a bigger mass. So what I did here is I said for orange and blue, I'm going to put mass on top because it's mass divided by volume, and I just wrote the word big because the orange has a bigger mass, and then I wrote the word small for blue because it has a smaller mass. It's higher up on the scale. So that's how I figured out the mass, is by looking, this guy is down farther, so this orange has a bigger mass. Then we know we need to divide by the volume, so I'm looking at the size of the box, right? Volume is the amount of space. Well, the orange box is clearly smaller, so I wrote the word small, and the blue box is bigger, so I wrote the word big. So now let's think. If I take a big number, like 100, and divide it by like a small number, like 1, I'm going to get 100 as my answer. What if I do it the other way? What if I take a small number like 1 and divide it by a big number, 100? And again, I'm making up these numbers, but in my head, I'm thinking big versus small, right? So who's going to have a bigger result if density is mass divided by volume, 100 divided by 1 or 1 divided by 100? Well, we get 100 or we get 0.01. I clearly see that, no, that's right. Okay, I clearly see that the bigger number is going to be the orange block. It has a bigger density because it has a big mass over a small volume. I did the same thing on this guy. The big mass, the heavier one, is the orange, so big and then small for blue. And on the bottom of my equation, I have a big box for orange and a small box for blue. Well, if I take a big number like 100 divided by another big number, I get 1. If I take a small number like 1 and divide it by a small number like 1, I get 1. Okay, and again, I made those numbers up, but the whole point, that's not necessarily that the volume and the mass are the same, but the whole point is we cannot determine on this one. We would need more information. We would need more specifics, like the exact volume or the exact mass. An actual reading, we can't tell just by looking. Okay, so I want you to pause the video and tell me for C and D which ones you think have the bigger density. All right, so when I went through these, I noticed that I used the word equal because on this one, the volume, or the masses are equal. And so I got the blue would have the larger density because like the top number is not changing. So really I'm just focusing on the difference in the volumes. When you divide by a smaller number, your result is bigger. So you can test that in your calculator, divide by some small decimals, you'll see your result is bigger. And then for this guy, we have equal volume, so the bottom number is going to be equal, so that's really not the factor we're paying attention to, it's the mass. And so when you take a big number divided by whatever, something equal, you're going to get a larger result. So for both of these, C and D, I got the blue has a bigger density. We can think about density through graphs, okay? When you do math class, and your teacher gives you a graph, they might ask you to find the slope. And there's an easy way if you have a nice graph paper or nice piece of graph paper. We usually say it's the rise over the run or the y divided by the x. Hopefully that sounds a little familiar to get the slope. Well, what if I put some units with these? So what is my y-axis? Well, that's the mass. And what's my x-axis? It's the volume. Mass over volume, or mass divided by volume. What if I put units? Mass is grams divided by milliliters, or grams divided by centimeters cubed. So what we're saying here is on a graph where you have mass on the y-axis and volume on the x, this is a graph where the slope is the same thing as the density. So what substance, A, B, or C, has the bigger density? That's going to be substance A. What has the smallest density? That's going to be substance C. Let's pretend for a second this guy in the middle, B, is water. What I know based off just peeking at this graph, substance A is more dense than water, which means it will sink in B. And substance C is less dense because it has not as steep of a slope than water, so it will float in substance B, which is water. So just some information you can gather from these graphs. On this slide, I have a chart for you of different substances, what state of matter they are in, and then the density. So density is known as a physical property, so every substance has its own unique density, and if I can figure out maybe the mass of something and the volume of something to solve for density, I can figure out what the substance is. So let's say I have an unknown substance, I measure the mass of it, I measure the volume of it, I can then match, when I do that division, whatever it might be and say, oh wow, that's iron based off the density. To this guy, let's find our pure gold right here on the bottom. It's 19.32. Density is called an intensive property, which means it does not depend on how much we have. So here's some water in a big jug. If I pour it into a cup or I take a little droplet of it, assuming this is all pure water, all of it has the same density. Okay, water is always the same density. It does not matter if I have a whole jug or a small glass or a small droplet, always the same density. And then this guy is saying that the higher concentration of solute, which is anything dissolves stuff, then the greater the density of solution. So let's pretend I make my morning coffee, and I put a spoonful of sugar in that coffee. That solution, that mixture of sugar and coffee, has a higher density than the pure coffee. What if I have one, or maybe Mr. C, Mr. Travella, he doesn't really like coffee, but we'll pretend. He has a cup of coffee, but he puts 2 scoops of sugar. Well, this one will have a higher density than the first one because it has more solute, more dissolved stuff. So One thing that I will want you to memorize is that for water, 1 milliliter is the same as 1 gram. And so water has a pure water, I should say, has a density of 1 gram per milliliter. Okay, and then just so you guys know, for these problems that we're going to solve, 1 centimeter cubed is the same as 1 milliliter. Okay, so if I measure something using a grad cylinder, or I measure something length times width times height, we're going to call these guys equal. So you might see density as with this unit or this unit. It doesn't really make a difference for us. All right, so aluminum has a density of 2.7 grams per centimeter cubed. What is the volume of a piece of aluminum that has a mass of 3.45 grams? All right, so we know density is mass divided by volume. So we have the density 2.70 grams per centimeter cubed equals. They gave us the mass of this piece of aluminum, 3.45 grams, and they want to know what the volume of this piece is. That's our question mark. So I'm going to just put V for volume because that's what we're solving for. And when we solve, our units hopefully will cancel. So I'm going to solve this by doing, if I put this whole thing over 1, so it looks like a fraction equals a fraction. Now we can do that really fun thing your favorite math teacher taught you, where we cross multiply those, and then we crisscross here. Okay, so what I'm going to end up getting is 2.7. Oh, redo. I'm going to get 2.7, and that has a unit of gram per centimeter cubed. I'll keep that whole thing in parentheses, times V equals 3.45 grams times 1. Okay, obviously, no, we don't need to write that times 1. I'm just trying to make a little algebra statement for those of you who are a little rusty. Okay, so now to get V by itself, we have to divide both sides by 2.7, and that unit stays with it. Divide both sides, 2.7 gram per centimeter cubed. So what we see here is these guys cancel, so I'm just left with volume equals, and on this side we get 3.45 divided by, oops, that's grams, because divided by 2.7 grams per centimeter cubed. So what I'm seeing right now is on the top of my fraction I have grams, and on the bottom I have grams. So those guys are going to cancel, and what I'm left with is volume, volume equals the result of this division. So I end up with like 1.277, so 1.28 with sig figs for my 3 sig figs, 1.28. And then what we see here is that centimeter cubed is on the bottom of a bottom fraction, so that's just centimeters cubed. There's my final answer. All right. So Samantha has some cheapskate boyfriend. He gives her this ring, and he claims that it's pure gold. That's 24 karat gold, pure gold. But she doesn't quite believe him. So after chemistry class, because she's a nerd and she doesn't trust her boyfriend, she measures the mass of the ring, and she finds the volume by something called water displacement, which I'll talk about in a second, to find the density of the ring. Because she knows that if she can find the density and if it matches pure gold, then her boyfriend's being truthful. If it does not match the density of pure gold, that means it's partially gold, hopefully, or not, but it's made with other things which are probably less expensive than gold. All right, so I drew some pictures so we can look at her data. So she first found the mass. So all she did was plop that gold ring on a balance. Okay, then she filled a graduated cylinder, and she recorded the initial volume of water in the grad cylinder. Okay, so she probably just filled it up partial. It doesn't really matter how much is in there as long as she records exactly. And then what she does is she puts the ring in the graduated cylinder. Okay, for those of you who have ever taken a bath, or I guess the swimming pool is hard to tell, we'll go with the bathtub. Okay, I know you know what happens. I don't know why I think of this, but I always think of like President Taft getting in the bathtub. He was like one of our bigger presidents, you know. I don't know why that visual comes to mind, but picture this gold ring jumping in the bathtub, President Taft jumping in. We know that water level is going to rise, so she measures then the final volume. Okay, why is that helpful? We can find the volume of the ring by doing a little difference, a little subtraction. So if I take the final volume, 43.7 milliliters, minus the initial 42.2 milliliters, okay, we're going to use our subtraction sig fig rule, so one spot past the decimal, we should get, let's see, 0.8 plus 0.7, nope, I lied, 1.5. Yep, hopefully that's right, milliliters as the difference. All right, so we know that density of the gold ring, or gold, I should put air quotes, is going to be equal to the mass over the volume. Well, we have the mass, 15.28 grams from the balance, and we have the volume of the ring, right? I don't care about these volumes anymore. I just care about the ring volume, 1.5 milliliters. So I get a density equal to 10.186 blah, 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 blah. I'm going to put that into 2 sig figs because we're limited in division by the weakest link. So I have 10 point as my density, and the unit is grams per milliliter, right? Those don't cancel, grams per milliliter. So how do we know if this is helpful? Like 24 karat, that's carat is not a unit of density, but we know what pure gold is. So I'm going to flip back if I can. Is 19.32 the same as 10? Nope. So what that tells me is she should throw it at him. He was a liar. It is not pure gold. All right, this one's pretty easy. I want you to try. I want you to tell me which has a greater mass, 19.3 milliliters of water or 1 milliliter of gold. So pause the video and then you can check your answer. All right, so I took the density of water. They have more specific on this chart, 0.9982 instead of the 1.0. I used what they gave us. And I said, so that density is equal to the mass divided by the volume. So we're looking for mass, and then the volume. I know they said 19.3 milliliters. I just kept it as centimeters cubed, so that way our units cancel out. Remember, they're interchangeable for these problems. And then what you can see is that when I cross multiply, and then mass times 1, so I didn't put that anymore, the units, centimeter cubed, is on the bottom of this fraction, and then on the top here, those cancel, so we're just left with grams. I did get something like 19.26, but with sig figs, we can only have 3 sig figs because of that 19.3, so it ends up rounding to 19.3. Same thing with gold. I found the density of gold, and then I changed that 1 milliliter to the centimeter cubed unit. That way those units cancel. And also with the 3 sig figs, I got 19.3. So in this case, they actually have the same mass. 1 milliliter of gold is the same mass as 19.3 milliliters of water. All right, last one. Density of osmium, which is the densest metal, is 22.5 grams per centimeter cubed. If I have 1,000 gram block of this stuff, and they're telling me 2 dimensions of it, so one dimension is 4 centimeters and the other dimension is 3 centimeters. We want to know the third dimension, the height, so to speak, of the block. Okay, so here's what we know. We know that density is equal to the mass divided by the volume. In order to find this yellow missing side, we'll have to find volume. So let's solve for volume. 22.5 grams per centimeter cubed is equal to the mass, which is 1,000 grams, divided by the volume. So I'm going to do a little crisscross, 22.5 grams per centimeter cubed times the volume is equal to 1,000 grams times 1, right, if we crisscross. And so now I'm going to do a little division to get the volume by itself, or get V by itself. So those cancel with 1,000 divided by 22.5 gave me volume equal to 44, and I get 3 sig pigs, so 0.4 centimeters cubed. So that's the total volume of this box. Well, in geometry, we know that the volume is equal to the length times the width times the height. So we have volume. 44.4 centimeters cubed, and they gave us the length, the width, and so we're looking for the height, which is that yellow piece. Okay, so we can kind of solve this guy real quick. 44.4 centimeter cubed equals 3 times 4 is 12 centimeters squared times the height. And we'll divide by 12 centimeters squared. And that gives me a height of 3.7, and we get 3 sig figs, 3.70 centimeters. The reason it's just centimeters is because over here, centimeter cubed is on top, centimeter squared, so 2 of those centimeters are going to cancel out. We're just left with 1, which makes sense for a height. Very good. Hopefully this helps. Come to class with questions on density.